Okay, it's, it's time to start. Uh, Good afternoon, everybody. This week we will start the first our large language model, which is called BERT. BERT. So I think you recognize this character here. But before we will talk about BERT, we will talk about ELMo, which was the previous language model. So last time was kind of covered transformer for translation, and um, let's talk about what happened like in between 2015 and 2019 when BERT was proposed, and GPT at the same year also was proposed. And then we will talk about BERT, and on Wednesday we will actually work with BERT and fine-tune it. Okay, so on the first lecture, we talked about word embeddings. And as you remember, um, in your homework two, if you use word embeddings, then it speeds up the training of your model. And by the way, I finished grading last night homework 2. And I believe those guys who used several convolution layers noticed that this actually worked pretty good. So instead of just one convolutional layer, use 2 or 3. And I think it was the most efficient model. Of course, attention worked and other RNNs. So the idea to use something pre-trained is called transfer learning. We kind of train word embeddings, but then we reuse this pre-trained word embeddings, for example, for text, for sentence classification. And we will talk today about 2 main ideas that brought us to the current state of the NLP. So yeah, this is just the reminder how we could use word embeddings trained from scratch or use pre-trained and or combine these 2 approaches, initialize our weight by pre-trained and then continue to training these embeddings. This is the idea of transfer of knowledge, transfer learning. So in transfer learning, we kind of used one model to train another model. And there are different ways to do this. One is called transducive transfer learning, when we use the same task, for example, named entity recognition, but use, for example, different data set. Another approach is called inductive, when we stack different models we use pre-trained word embeddings and use them in different models. So you don't need to remember this, it's just for your information. So this is the idea of transfer learning. So in word embeddings, we use word embeddings for a task-specific model. Or we could use and train embeddings from scratch, but the model was the same. So the first great idea was to use words, but context aware. Word embeddings also context aware, but they were trained on general corpus. But now we want to create embeddings that are aware of our sentence, specific sentence. So, and this model, I will skip this slides. So this model, first model that used the sentence-specific word embeddings is called ELMo. So, and this is the first great idea to use word embeddings, but specific for our context. Then we will talk about the second idea. So the idea of this ELMo was to use some model that creates embeddings that will actually look at the input sentence. And after that, use this embeddings for a specific task. So this is the pipeline, or we can use general embeddings and then train a specific model, or we can use our auxiliary model that will create context-aware embeddings, and then we can use this context-aware embeddings in our model. So this is the idea of ELMo. So this model was proposed in 2017, but got the best paper award on 2018 conference. And this was the first depression time in NLP, and I will explain later why. So they created the embeddings for tokens, but character-wise. So you could create a dictionary of embeddings for every character, and then use a convolution layer to create embedding for the word. So what do you think, why the character level embeddings are better than just token level embeddings? We also talked about BP, like part of words embeddings. They also are better than entire token embeddings. So can you think about the advantage of using these part of words or character level embeddings? Yeah.
there's very few characters, but a lot of words and tokens.
Yes, so reduced size, but another reason it takes care of the typos, because if you make a mistake in one character, the entire embedding still, unless you still will be close to the expected word. Okay, so and then after creating for each token this character level embedding, they propose to use two LSTM layers. One LSTM was forward, another LSTM was backward, and then they stacked the outputs from hidden vectors for this LSTM, concatenated this, and this concatenated vector they used as the context-aware embedding, because LSTM kind of looked at all the tokens, so that's why the output has information about the input sentence. And so, in other words, this word cat will actually have information about that it was on a mat. So then we can use one more layer with this LSTM. And finally, they took the weighted sum of input embeddings, like general embeddings without information about the context, and embeddings from the first layer and from the second. And this works so nice that all the many papers that year on the conference were rejected because they asked reviewers asked to check ELMo embeddings, and when they tried ELMo embeddings, their model actually underperformed than just using context-aware embeddings. So this was bad time for people working with such tasks like entity named entity recognition or part of speech tagging. It didn't affect translation because in translation they used attention mechanism. So so this was the first great idea, to use context-aware embeddings. The second great idea was, but we used a different model for different tasks, like one model for translation, another model for named entity recognition, and so on. Kind of in your homework, you try different models and look which combination of layers works better. The second Great Depression came next year in 2019 with BERT model, when one model actually could be used for any tasks. So this is the second idea, to use one model for all NLP tasks. So if in case of ELMo, we used ELMo as input to the to our model with BERT or GPT model. We just use this model. One model for all the tasks, for document classification, for information retrieval, for every task. And again, researchers who just played with different architectures of model, you can just add one new layer and voila, you have now the performance of your model. They remained without a job because now there was just one model which overperformed all other possible experiments of the researchers. So, but this was not the end of the story because in 2022, ChatGPT was introduced. And this actually, I believe, revolutionized the entire research because you can use ChatGPT to write papers, you can use it to understand papers. So people now try to come up with some policies. What is the research? How much can you use AI? So, but we will go to GPT next week. So it will be the third Great Depression in NLP. And of course, all conventional natural language processing methods, they were how to say, we don't need them anymore because models, large language models can understand the relationships between parts of speech, between different sentences. So all the work that was done manually before that or with count-based methods, they don't perform so well as GPT model. By the way, BERT can be carried on your cell phone, so it's not a very large model. Okay, so let's talk about BERT. I will skip GPT. We will talk about GPT next time, next week. So transformer. I believe last week, last Friday lecture was actually the most important in the entire class, the self-attention and transformer. So I prepared kind of review of this transformer architecture. So we have on input embeddings of words. And we represent these with columns, but in code, we represent them as rows. So of our matrix X, and in rows, we have embeddings of the tokens, but we represent visualize typically with columns. Then we applied three different matrices, linear layers, which we called query key and value to this vector matrix X, but technically to every vector in this matrix. And then we split this output into parts that we called heads. So I believe it's easier to see in this image. So we have three embeddings for every token, and then we kind of split this embedding into parts, and the number of heads here is H. So the size of embedding, if the size of embedding is D, then each head has the size D over H. So we have H heads. And after that, we apply attention to each head separately. So after applying attention, you remember in attention, we um, take a blue embedding, then we calculate the similarity with yellow embeddings, then we sum up the red embeddings with these similarities. So, and finally, we get the output from our attention, a new embedding for input token. So we apply attention for each head. So in my case, I have 4 heads. So after applying attention, we have 4 heads, attentive heads. And then we apply linear layer. We just concatenate these heads and apply linear layer. And all this is called multi-head attention layer. After that, we apply normalization. And as you remember, it's not a batch norm, because batch norm calculates average mean and average standard deviation to normalize each vector. But it's possible that in our batch, we have some phrases from the future. So to avoid kind of take into account some phrases from the future, we normalize every line of our batch individually. So that's why it's called layer norm, not batch norm, layer norm. It's not. It's to be honest, not clear. Maybe if they would use batch norm, it would work, perform the same. But traditionally, layer norm is used. After that, and the layer norm is applied to residual connection. We add the output from multi-head attention with original input. So after that, we pass this output through 2 linear layers, which is called feed-forward network, or it's the same as multilinear perceptron. So sometimes people call this feed-forward neural network, sometimes they call MLP, multilinear perceptron. So it's just 2 linear layers. That's why I kind of visualize with 2 different embeddings, one linear layer, another linear layer. And finally, we take residual connection from output from this FFN layer and the previous output from multi-head attention. Again, apply linear norm, a layer norm. And this is the output from our transformer layer. So this is one transformer layer. And in transformer, typically there are 12 or another number of these transformer layers until we actually get the final embedding. So I just wanted to, but you could notice that like in the translation, we used recurrent neural network. And the recurrent neural network actually takes care of the order of the words. Here we don't have this. So in transformer, we also should introduce so-called positional embedding. I didn't visualize it here, but in addition to input embeddings, we use also position embedding. I added the link. Let's see. oh, this is the Yandex course. I added the link to one transformer implementation, which was used to solve the problem of copying of a sequence. Just if you have input sequence, how to train a neural network that it will reproduce this input sequence. So, but you can see here all these layers implemented, like attention, multi-head attention, but also positional feed forward. So just two linear layers. But yeah, I want to show the positional embeddings. In original paper about transformers, they propose to use a vector of the same shape as input embedding, but the coordinates of this vector were calculated by these formulas. So it's sine and cosine. So for example, for the first and second, it's sine and cosine of 1, because I is 0, so it will be power 0. So then the third and fourth components will have the sine and cosine of current position divided by whatever number is that. So, but those were fixed numbers, fixed vectors, and you can, and we just add, and here is the representation. So this is the position, like time, and these are the coordinates of our embeddings. And you can see that vectors defined by this formula, they are different for every position. So kind of introduce the order information about ordering in our input. We will just add position embeddings to every token. And here is example how it's copied this sequence. You can see, wait a second, I believe after train. Yeah, so the expected sequence was just sequential numbers from 0 to 5, and the generated sequence has just one mistake at index 1. Okay, after this reminder of the transformer, we are ready to go to BERT model. So the BERT model is just the encoding of this transformer, encoder part of the transformer. So you remember in translation, we had encoder, decoder, and cross attention. So BERT is just the encoder. We have just multiple transformer layers in original paper 12. So the input to this model looks as follows. Two sentences. They are separated by special token SEP, And they have also introduced, in your dictionary, you can introduce embedding for new token. So they introduce new token classifiers, CLS. And one of the tasks was to classify if the second sentence actually is a continuation of the previous one or not. So it was binary classification task. So during training, they used 50% times related sentences, like the second sentence was the like the true next sentence, and 50% they changed the second sentence by arbitrary sentence. And the goal was to classify if the second sentence is a continuation of our phrase or not. So it's important to understand that you remember in translation, we used output embeddings for every word, and then we use the classification. We compare this with the true translation. So in BERT model, only first token CLS and separator were trained. So we used logics only for these tokens, but not only for this. So the second task, for which BERT was trained is called mask. But okay, before we go into mask, let's talk about the input. So in traditional transformer, we use the sum of BERT embeddings and positional embeddings. In BERT model, they also added the embedding for the number of the sentence. Like for all words in the first sentence, they used one embedding. For all the words in the second sentence, they used another embedding. So the second objective was MLM, masked language model. So let's talk about this now. So for input words, they choose randomly 15% of these tokens. So like in this case, these three words. Bless you. And in for this chosen words, you can see the so for 80% of words were covered or like substitute by another token mask. 10% of these tokens were changed randomly. And the rest 10% were not changed. But they were used in the classification. So the training of this model was based only on these chosen tokens and the first CLS token classification token. So in other words, in our loss function, we just use this 15% of tokens instead of all the output words. And for next token, this word embedding after all these transformer layers had to understand that it was actually this word. So kind of we forced this covered word to understand which word was covered. For the change word, we forced to learn that this word actually was a different word, that it was not the word T, but it was the word gray. And for the unchanged word, we still trained and we forced this word to learn its context, because in transformer there are multi-head attention layers, and these multi-head attention layers actually looked at other embeddings, and also we will talk later about feed-forwards layers. They also learn what is the most probable next token. Okay, so this is the training objective of this BERT model. And this slide represents the difference between language model and this masked language model. So in language model, we train our model to predict next token. In masked language model, we train our model actually to understand the covered word, for example. And you can understand maybe even now how we can use this model for like question answering systems. For example, you can formulate the phrase like Fibonacci was born in, and then use mask. And large language model, BERT, actually will understand that that mask should be the year when Fibonacci was born. So I hope now you get the idea why one model is used for any tasks in NLP now. Well, typically GPT, but BERT is the first model. Okay. Yeah, the other application of BERT can be also wait a second, what is that about? Yes, this is actually example how we can use this BERT for question answering. For example, you can train your BERT model on the pairs of sentences, where one sentence is the question, the second sentence is the answer, and for example, classifier will be trained like 1 if the answer is correct and 0 if it's incorrect, or for similar questions. So this is question pairs, and you will work with this data set for next homework, fine-tuning BERT to find similar questions. Okay. So yeah, we'll go back to our original idea that instead of using the embeddings even context aware for as input to a new model, now one model is used for any task. Um, and so this happened in 2019, and after that, it was. And I know some people still are very skeptic about large language models. I mean, people working in NLP because they don't understand them, and they used to work with conventional methods. So it was time of the um, projection, then negotiation, and then acceptance. So finally, people, most of them, I can't say all, but they realized that this is the new paradigm in language processing. And in 2020, on the conference NACL about natural language processing, the new section was introduced analysis and interpretability of large language models. So people started trying to understand actually why this model works and what it learns and how can we um, make this model to perform desired task. So let's talk about interpretability of BERT. And as you remember, there are two ways to assess the model. Model specific. In this case, we look at the neurons inside the model, what they learn, and model agnostic, when we apply this model to different tasks. So let's talk about first model specific or intrinsic evaluation. So if you look at the attention maps for each head, you remember in the case of translation, we saw attention between the words in one language and words in the other language. In this case, it's self-attention, like input text. And but we have different heads, and we can print attention uh, probabilities for every head. And in, for example, first head, you can see that the most attention is on separator, and it makes sense because the model should understand kind of which token belongs to the first sentence, which belongs to the second. In the other diagonal, so it's kind of self-attention. In the other attention map, it's a combination with emphasis on separator and itself. On the other attention head, it's interesting, it block attention, so it's kind of, it learns if the word belongs to the first part of our input. And some less informative for us, but maybe informative if you will look like closer in this attention maps. So for example, here is connection between noun and adverb. So some kind of higher level linguistic properties. Okay, it's 1 minute left, and there's a lot. I think just we just pass through half of slides, and the second half is all about interpretability of BERT. So let's stop here for today. Yes. So maybe we will start next time. Finishing this slide, and then we will go to the coding. Yeah, and if you have seen my announcement, I learned that you can use up to 30 hours GPU on Kaggle for free. So next time I will code in Kaggle notebook. I mean, we will import BERT, and of course we will need GPUs to run it faster. Okay.